Okay, everyone. Hi, everyone. I'm Teacher Charlotte. So it is 5 past now. So let's begin. So I think the majority of you are already here. If anyone's late, I can just let them in later. So well done for those that showed up exactly on time today. And thank you for being so patient in waiting for us to begin. So welcome to the first of our science lessons throughout the school holidays. So this is the first of 4 science lessons throughout August. So welcome to the first lesson. Okay, so let's start off with getting to know everybody. So what I want you to do is tell me in a minute, or you can write in the chat. It's entirely up to you. You can unmute your mic or write in the chat. Tell me what your name is, how old you are, where you are from, and you could even add a hobby in there if you wish. So I'm going to write that down to everyone. So number 1, name. Number 2, how old are you? Number 3, what did I say? Where are you from? And number 4, have you got a hobby you want to share with everyone? There we go. I'm going to give you all a minute each to do that. And hopefully you can write in the messenger chat on Zoom so I can read it all. So we've got Azia. Am I saying that correctly? Azia? Azir? And then we've got Hamna. I hope I'm pronouncing that correctly. If I'm not pronouncing your name correctly, just shout, just tell me. Oh, we've got a few from Birmingham. We've got Hamish. Isaiah, is that correct? Isaiah? Give me yes or no, Isaiah, if I'm saying that right.
Isa's my sister. You say it Isa.
Isa, is that right? So we've got Daniel, who's nearly 13. He's in England and he likes gaming with Thrustmaster. Excellent, gaming. So we've got a gamer. Okay, good stuff. So a little icebreaker. Hopefully throughout this, we'll get to know each other a little bit more. So today then, how science works is what we're looking at. Now, because this is Key Stage 3 science, what that means is some of you are in, obviously you can see your ages there. Some of you are year 7, year 8 and year 9. Okay, so throughout this lesson, we're going to go for a few different topics actually. So I can see, as I don't know any of you or know where you're at, so I can see what you all do know and what you don't know. So we'll be covering a few different topics. If you're in year 9, it's more than likely that you have covered this before and that it's more of a revision lesson and you will know some of this, hopefully. But if you're year 7 or year 8 in September, some of this could be brand new. Thank you, Sam. Sam's nearly 14 and he is living in the United Kingdom. Excellent. So lots of us are in the UK today. I'm also in the UK, by the way. Okay, so yeah, going back to that. So if you're year 9, it's more of a revision lesson. Year 7 or 8, this could be brand new stuff to you. So don't panic if it is. We're just going to go through it at a nice slow pace. Okay, keep it simple and yeah, and hopefully we can have some fun along the way. So today we're going to look at theories and evidence. So how science works. We're going to first start off with what a theory is and how theories come about. Okay, so I'm going to give you all 60 seconds, so only 1 minute, 60 seconds. Have a little think to yourselves, what is a theory? Now you can start typing your answer in the chat if you feel confident enough and you think you've heard of a theory before. That can be an example of a theory, or you can explain what a theory is. Okay, 60 seconds. If I haven't got any answers, then I might have to ask some of you for an answer. Okay, 60 seconds, go. I'm liking some of these answers. Well done. 40 more seconds. Got 3 answers so far. Well done, you guys. I'm not going to comment on any of the answers just yet. let's say 30 more seconds. Fifteen more seconds. If you're typing an answer out, get ready to send it. Okay, and we'll hold it there. So some good answers in there. So someone's put an educated guess. Sounds quite good to me. Someone's put it's a myth or a guess as to what a subject would be. Someone's put an educated guess, okay, a sensible guess, and someone's put an educated guess based on previous knowledge before conducting research. Okay, now it is a mixture of all of these things. Has anyone got anything else to add? Does anyone want to unmute their mic? Feel free to do so. No? Okay, fair enough. Sam, a theory is a recollection of information to create an answer or a solution. Okay, that's interesting. Now, I'm not going to talk about this too much because this is what we're going to go through throughout the lesson. So hold your thoughts there at the beginning of the lesson. Okay, and then at the end of the lesson, we will come back to this question in a bit more detail. So theories in science then. The actual definition of a theory in science. Scientific theories are ideas which explain events. Okay, so across the course of this lesson, we are hoping to understand some of these following questions. Oh, sorry, my keyboard keeps doing that. So we're going to look at what makes a theory different from a guess, which is a good one, because some of you have said that a theory is a guess. Some of you have said it's an educated guess. Some of you have said it's a sensible guess. We're going to look at what theories are better, what makes a theory better than another theory. Some of you may already know that answer. And what are some examples of theories? And how can we use experiments to find evidence for or against a theory? Okay, so that's what we're going to look at. Sorry, I keep getting distracted by this little chat here. That's why I'm not in full motion. So you may have heard some theories a lot in the news before, some of you or in your science lessons. So you may have already heard or read of a theory. Newton invented his theory of gravity. Okay, you might have heard about the theory of evolution, and you might have heard the Earth is spherical and not flat as a theory. Okay, anyone heard any other theories? Now that you know these theories. So a controversial one, I would say controversial that you might have heard a lot in the news is the Earth is spherical and not flat, because there are some flat earthers. But why do you think that? Why do we think that might be different?
Because we know that the Earth is actually round due to like pictures taken by NASA and kind of.
Good. Yeah, I like where you're going there, Sam. So why do we think that? What makes us think that the Earth is spherical? What's there to support that?
Because of, well, we take like images taken in space, like say on the ISS, and it's showed as like almost like a curve of the world and like the spherical kind of. I can't really.
Yeah, good.
But, like, so you can see the kind of shape of, you know.
Good. Yeah. So there's scientific observations out there supporting evidence that the Earth is spherical. Okay. So that's what that theory is. And this is all theory. Okay. So a theory isn't a guess. A theory is something that's backed up by evidence. So some people do believe, some people are looking at theories that the Earth is actually flat, but you can weigh up that theory. You can go and look at the theories that the Earth is spherical, and you can compare that to the theories that the Earth is flat, and that way you can make your own decision on which theory that you believe in. Obviously, Sam is right. There is so much evidence out there that supports the theory that the Earth is spherical. Okay, there's plenty of mathematical research as well as scientific research that proves that Earth is spherical. Okay, so that's theory. So on that, so it's important to note that a theory is good when it can be explained by events well and is supported by evidence, what we were just talking about. So those of you that aren't quite sure on evidence, okay, evidence is our information which can be used to support or disprove a theory, okay? Now, so where does the evidence come from? The evidence comes from an experiment, and that can be either a measurement, so you do measuring in experiments, it can be an observation, like Sam just said, there's pictures from space, so that's an observation on people who've obviously gone to space, they've gone to the International Space Station, they've said that they can see the curvature of the Earth from the space station, so that is an observation, example of an observation, or through counting during your experiment, okay? Don't worry, I know. So today we're going to discuss a theory, okay? So we're going to look at a different theory, not one that I've already spoken about. We're going to look at a different theory today. And that theory is going to be the conservation of mass, okay? Oh, as I've just seen your message there. Sorry, I didn't reply to it earlier. So yeah, the theory of the conservation of mass. So, but first, before we delve into this theory, okay, what is mass? Does anybody know what mass is? You can type it in the chat or you can unmute your mic. Feel free to do whichever it is you would prefer. Have a little think. I'll give you 30 seconds as well. Have a little think. What is mass? Oh, I like that. A large body of matter. How heavy things are. Good. Anyone want to add to those two answers? Using the word matter in our answer. I love that. I'll give you 10 more seconds just in case someone is typing out an answer. Don't want them to miss out. And we've even got a little joke in there. I like it. Okay, so I'm assuming you've already answered. So mass, yeah, those two answers are very correct. Well done. So the mass of an object is the amount of matter. Now, the person that has defined mass and they've used the word matter in their answer, do you know what matter is? What is matter? Because there might be some year 7s or year 8s here that might not know what matter is. Or does anybody else know what matter is? They would like to answer that question. The atoms and molecules that form it. Very, very good. So the atoms and molecules do form matter, okay? Matter is something that's all around us, okay? Everybody is made up as matter, okay? My mug here that I've got on my desk, this is made of matter, okay? My body, I am made of matter. Everywhere around us, everything is made of matter. What's everything is made up of? Yeah, that's very right. Very good. Oh, year 7. That's very good that you know that. Well done. Not many year 7s know that. So the more matter an object contains, the greater its mass would be. Okay. So I've got a little example there. For an example, an elephant, sorry, getting my words muddled up there. An elephant contains more matter than a mouse. So we should all agree that an elephant has a greater mass. Okay. So nice and easy, nice and simple. You have a huge brain. Okay. So, oh, actually go back. So does anybody know what mass is measured in? You might have just saw my answer there. So we're still on the topic of mass. How do we measure mass? Kilograms. Yeah, be careful there because I've seen you put newtons first. Well, someone's put newtons. Does anybody know what is measured in newtons? Does anyone know that word? So we don't get confused. Weight, yeah. Weight is measured in newtons, okay, because that's all to do with gravity, which we will come to on another day. But mass is measured in kilograms, okay? So really important there that mass in science, mass and weight are different things, okay? So be careful not to get mixed up with those words there. Good. So what's that saying is, so oh, I wish I do not weigh 5 kilograms, but let's say more of my body weight, my body mass. So my body mass is about 70 kilograms, near so 70 kilograms. So if I weigh 70 kilograms now, if I went to the moon, if I was lucky enough to go to the moon, I will also, my mass would still be 70 kilograms. Okay, so my mass does not change. Okay, now I know some of you might be, well, actually, you could lose mass if I was to lose some body mass by dieting or exercising. Yes, you're right. But if I'm sat at my chair here, my mass of 70 kilograms stays the same whether I stand up, sit down, or walk out in my garden. Okay, so my mass is still the same. Yes, we'll come to that. Yeah, well done, Isaiah. Yeah, your weight would change if obviously you went to the moon, because weight is different. Weight is measured by gravity, but that's another topic. So we are getting on into a little task in just a minute. Okay, I'm aware that I'm rambling on a bit now in the lesson. Okay, but so our theory of the conservation of mass then, okay, this is the idea that atoms are not created or destroyed in a chemical reaction and only rearranged. Okay, this theory says that the total mass of the reactants and products must be the same in a chemical reaction. Now, because we're all different year groups, I want to break this idea of this theory down a little bit. So I want to delve into it. There's a lot of scientific words in this theory, so I just want to break down these scientific words so that we all know where we're at in this theory. Okay, I wouldn't usually do this, but as we're all different age groups, let's just break down this idea. Okay, so first, what are your thoughts about a chemical reaction? Does anybody know what a chemical reaction is? Or give an example of a chemical reaction that is easier. So let me give you 60 seconds, okay? 60 seconds, write your answer of a chemical reaction in the chat. Or if you're feeling confident, you can unmute your mic and tell me, okay? 60 seconds, what is a chemical reaction? Okay, I've got an answer coming through on the chat. I'm not gonna talk about it just yet till we've got everybody else's. Got one answer. Does anyone else want to explain what a chemical reaction is or give an example of a chemical reaction? It doesn't matter even if you're not sure and you're just listening in and waiting to find out. Some of you might not know a chemical reaction yet. As I said, some of you may be in different year groups and you've all been to different schools as well. So you might be on different stages of the curriculum, which is good that you're all here today. Okay, good. Say 20 more seconds, just in case you're writing your answer. Okay, so we've got the rearrangement of atoms as an answer, and when elements are reacted with each other. Now, that is we're going to get onto that. Okay, so those answers are on point there nearly. So let's have a look now. Now I'm going to give you a bit more clues as to what a chemical reaction is. So on your screen there should be 4 photos. Okay, so we've got the car. We've got a bike with a chain. We've got a match that is been set alight. Okay, and we've got, this is the more tricky one. So this is more probably a higher level, maybe more of the year 9s. But we've got a plant, and you can see some sunlight in the background there. So now that I've put these 4 photos, they are all to do with chemical reactions. Okay. Can you? Okay. Oh, actually, it should be one. Hold on. So what, number 1, number 2, number 3, number 4. So in the chat, write your answers, okay, you can describe the picture or explain why that picture is a chemical reaction. Somebody's already done number 4. Try and submit all your answers 1, 2, 3, 4 at the same time. Otherwise, we'll see. Actually, sorry, I've just realized. Send them to, so for this task, send them to me personally. So in the chat, you should be able to send me a personal message, a private message, so that not everyone can see your answers. Okay? Otherwise, it's easy for everyone if they can see your answers. So I'll tell you what, I'll give you 5 minutes from now, okay, to answer question 1, 2, 3, and 4. So all we're doing is seeing if we can figure out what the chemical reaction is by using these photos. So think carefully about the photos, what has happened to make a chemical reaction. Got just under 4 minutes, guys, okay? Got some good answers coming through. So most of you have done number 3 and 4, which is really good. Can we dive deeper? What's happening in number 2? What's happening in number 1? Think about what cars burn. What do you put in your car? What are you burning in your car? And this one, number 2, simply look at the picture. What's happened to that chain? When you buy your bike brand new, does your chain look like that when you buy it brand new? Or over time, what does it do when it's sitting in your garage and you're not riding it anymore, or it's sitting in your shed, or you've left your bike out in the rain, for example? What will happen to it? Okay, I am reading your answers. They're coming in, by the way, so just keep your answers there so you've got a record of it when we go through the answers. Okay. Okay, should we say 1 more minute? 1 more minute. Get ready to, if you haven't already sent me your 4 answers, send them over. If you've got unanswered questions, it doesn't matter. Okay. Okay, so number 1 then, some of you have got there now. So it is something to do with fuel. Yeah, you put petrol in your car, you put diesel in your car. Okay, so number 1 is the burning of petrol in car engines. So that is the chemical reaction in there, the burning of fuel in your car. Okay, number 2, did we get any answers? So someone has put its metal reacting with air, so it becomes rusty. Yeah, it is reacting. Okay, so this is the rusting of steel on a bike chain. So the metal there is still rusting on a bike chain is the chemical reaction. Number 3, did some of us get this? Combustion exothermic, yeah, good. So this is a burning of a match, just simple. The burning of a match causes a chemical reaction. Okay, so when you light that match, there's an oxidization that causes the chemical reaction. And then number 4, some of us got this straight away, well done. That is photosynthesis. So what's the does anyone know the chemical reaction in photosynthesis? Okay, not sorry, because actually we're going to look that up in more detail in a couple more slides. Okay, so chemical reactions, they happen every day, and these four examples are just real life examples of chemical reactions happening around us every single day that we should have all, I'm sure we've all seen rust before. Okay, we see cars are all around us, we light matches, and plants are all around the world. Okay, so there are millions of reactions taking place every single second of every day. Okay, so that's just chemical reactions there. Okay, so chemical reactions involve the production of one or more new substances called products. So going back to the definition of the chemical reaction, okay, involves production of one and more new substances called products. So they're all products. So how, looking back at those 4 pictures that we just discussed, okay, how can you tell when a chemical reaction has occurred? So use those 4 pictures to help you. What has happened in those 4 pictures that you can tell? There's 2 pictures there that should give you the answer sort of straight away, give you more of a clue. How can you tell a chemical reaction has occurred? Send me your answers privately, please. Look at the pictures to help you. I'll give you 2 minutes. Short one, 2 minutes. How can you tell by looking at those pictures that a chemical reaction has occurred? So the person who's put it changes or something happens, I need a bit more detail in that answer. They are right, something is definitely changing, something is definitely happening, but use those pictures to help you what is happening. Minute and a half. How can we tell when a chemical reaction has occurred? So what changes? Just under 60 seconds, and then we'll go through the answer of how you can tell a chemical reaction has occurred. Okay, so let's have a look. Some of your answers are looking good there. So how can we tell a chemical reaction has occurred? Okay, well, look at the pictures, okay? Oh, so it's the signs of a chemical reaction has occurred include color change. So the steel turning to rust, that's the change in color, isn't it? A gas being given off, okay? Sometimes obviously you can't see that in the car, but it's something that we know, and photosynthesis as well, gas being given off, or heat. So with the match, you'd be able to feel the heat, okay? Or it could be a solid forming is a sign of a chemical reaction, okay? So in those pictures, the color, we've seen color change, we've seen heat, the gas in the car, and the plants, okay? So that's how we know a chemical reaction has occurred. Okay, so now let's look, okay, so I've put our theory again that we're looking at in today's lesson, the theory of the conservation of mass. But as I said, let's just break down these scientific words in this idea of this theory first. So now let's look at the reactants and products. Okay, so in science we use word equations, okay, to show what is reacting, and they're called the reactants. And then the new substances produced at the end of the reaction are called products. Okay, and the way that we display this is in science is by these word equations. So it's reactants equals, they use an arrow, okay, into products, and that's a simple word equation. So those chemical reaction photos that we just looked at, okay, we're going to look at what is a reactant and what is the product. So first, let's take a look at that car. Okay, what is the reactant in the car and what is the product? So the chemical reaction is obviously the fuel burning in the car. So what is the reactant and what is the product? Does anybody know? So what do we put in the car, for example? Fuel equals energy. That's nearly there. Well done for trying. Fuel equals energy, nearly there. So we put fuel in the car. What does the fuel react with? What's in the air? Do you know? In a car, the fuel is reacting with what? Let's have a look then. Oxygen. Yeah, well done. Isaiah, I think I just said that right. And Hamish, well done. You both sent that in at the same time. Yeah, oxygen. So fuel plus oxygen. Okay. And does anybody know what that reacts with to produce a product? What are cars known for giving off? Gas, yeah. Which gas? CO2. Yes, that's correct. So if you don't know what CO2 is, that is carbon dioxide. Okay, but also some of you may or may know that that is plus water as well, carbon dioxide and water. Okay, so this is the word equation, okay, for the reactants and products of this car. So fuel plus oxygen equals carbon dioxide and water. So in this word equation then, what part is the reactant and what is the products? Can someone tell me, just so I know that we're still on the same wavelength, so I know that you're all listening. So what part of the equation is the reactant and what part of the equation is the products? So fuel and oxygen is the reactant, carbon dioxide is and water is the product. Okay, just one last one before we move on, just to see where we're all at. So going to the photosynthesis. Okay, what does anybody know the word equation for photosynthesis? So think about plants. What do humans breathe out? What do plants sort of take in? And how do you keep plants alive? What do plants need? I'm going to give you 1 minute. So plants move something from the atmosphere. And in the summertime, we have to give plants lots of, when there's not much rainfall, what do we have to give plants lots of?
Water.
Good, well done. I think that might have been Sam that said that. Well done, Sam. Yeah, so the first part of the word equation is carbon dioxide and water, okay? We breathe out carbon dioxide and we breathe in oxygen, breathe out carbon dioxide. But that's good that we're breathing out carbon dioxide because the plants take it all in. And in the summer months, we have to give our plants lots of water. So yeah, carbon dioxide plus water is the reactant. And what is the product? Sugar and oxygen. Let's have a look. It's glucose and oxygen. So yeah, glucose is like a posh scientific word for sugar there. So you are kind of right in the sugar, but in science, we refer to sugar as glucose because that's the reactant. So we have our reactant in this equation and we have our products. There we go. Excellent. So word equations like these are used in a lot of science as a quick way of representing a chemical reaction. Okay. So Now back to now we've spoke about those key scientific words in this equation. Sorry, not in the equation, in the theory. So the theory of the conservation of mass. Okay, remember this is the idea that atoms are not created or destroyed in a chemical reaction, only rearranged. This theory says that the total mass of the reactant and the products must be the same in a chemical reaction. In other words, the matter cannot be destroyed or created. Okay, so we know what reactants now means, and we know what products means. Okay, and we've also looked at chemical reactions and mass. Okay, so this theory of the conservation of mass is a theory by a gentleman called Leviosa. Now, if you're a fan of Harry Potter, you might remember that word, Leviosa, from Hermione Granger when she says Leviosa. Anyway, that's if you've seen Harry Potter before. So this gentleman, Leviosa, he did hundreds of experiments, okay, into the theory of the conservation of mass. Okay, and we're going to look at this in a little bit more detail. Okay, so let's have a look. So the mass of the reactants and products must be the same in a chemical reaction. In other words, matter cannot be destroyed or created. So what that little bit means there that I've highlighted, that just means that mass is always conserved. Okay, so let's think of an example where mass should be or may be conserved. So think of when, okay, on a hot summer day, you might have ice, okay, in your drink, in your cup. So if you've got a cup of ice on a hot summer's day, what happens to that ice? What does it do? Thank you, Hamish. Well done. It's going from a solid to a liquid, isn't it? So the ice is melting from a solid to a liquid. Yes, correct. It melts to water. Okay, there's a little picture there. Very well done. Solid to a liquid. Okay, so here's my glass, for example. I've filled this beaker with ice. Okay, the mass of the ice and the beaker at the start of this experiment, okay, was 100 grams. Okay, so looking at this theory of mass and the reactants and products, okay, what is the mass of the beaker and the water after the ice had changed state? So the ice changes state from a solid to a liquid. Can anyone message me a private answer? What is the mass of the water in the beaker? So we know that the mass of the beaker and the ice is 100 grams. Now that the ice has changed state and gone to a liquid, what is the mass of the liquid and the beaker? I'm going to give you 30 seconds to send me your answers privately. What would the mass of the water and the beaker still be? Thank you, Isaiah. I've got your answer. Thank you, Amanda. Send your answers in. 15 seconds. So we know that the mass of the beaker and the ice is 100 grams. Okay, it's a hot summer's day. That ice has melted. Okay, it's changed state from a solid to a liquid. It's still in the same beaker. What is now the mass of the beaker and the liquid? 10 seconds. Thank you, Sam. Yeah, so what is the mass? It was 100 grams. So if you sent me a message saying 100 grams, yes, it's 100 grams. Okay, going back to our theory. Okay, this means that mass is always conserved. Okay, so in this little experiment, obviously we haven't officially done it ourselves, but we spoke about it theoretically. Okay, so can we all agree here that this theory approves? This experiment, approves this part of the theory. Well, yes, it does, because we know that our mass has been conserved in this beaker, changing from a solid to a liquid. Okay, now, what do we think, though? is this little experiment of ice, okay, ice changing state, is this enough evidence to support that theory today, though? And I've just copied that theory in again. Do we think that's enough evidence? Give me a yes or a no. There's no right or wrong answer. Could be. Okay, it's an experiment. Some of you have said yes. Yeah, it could be, because we have got some measurements, haven't we? We've got an observation, actually. We've got measurements of the mass, and we've got an observation that it stayed the same. Okay, but let's look at this theory in more detail then. Okay, let's look at another experiment, and we'll see if another experiment matches, approves that theory. So going back to our Leviosa, okay, whose theory that we're talking about today, of the conservation of mass, okay. Back a long time ago in the 19th century, okay, Leviosa said one thing. Leviosa said heating a substance will not change its mass, okay. Whereas another scientist and a bunch of others, Ernest and Stell, he said that heating a substance changes its mass, okay. These other scientists thought that the mass would decrease as some of the substance is destroyed. Okay, now let's look at those two in a bit more detail. Okay, so we can see if we can approve or disapprove Leviosa's theory. So Leviosa got to work. Okay, Leviosa wanted to do an experiment to test this theory out. And let's look at this in more detail. Okay, so what Leviosa did, okay, similar to what we've done, but this time instead of melting the ice, okay, Leviosa boiled the water instead. Okay, so we've already just looked at changing state from solid to liquid, but what about if we do the reverse and change state a different way? Now, I'm not going to say the word, okay, so instead Leviosa had 100 grams of water this time, and he boiled the water. He then let the steam travel through a metal pipe, as you can see here in the diagram, okay. The steam, he then waited for the steam to cool down, okay, and he weighed the water at the end, okay. So there's two questions there on your screen that I want you to answer. You've got 2 minutes. Number one is, what is the mass of the water at the beginning of this experiment? And number two, based on our theory of the conservation of mass, what would the mass be after this experiment, so at the end when the water has cooled down? Okay, send in your answers for number 1 and 2. 2 minutes. Send them privately if you can. So remember our theory that mass is always conserved. Okay, so if we're thinking about what our theory says, then what should it be at the end? 30 more seconds, just in case somebody's still typing their answer. I have got a few answers in already. Well done to those that have submitted. Okay. So yeah, number 1, I think all of you put, so the 100 grams, that one was nice and easy. It already says in our diagram, there's 100 grams of water. Now that's good. In your science exams, you will have questions like this, okay, that is asking you to look at diagrams and write down the mass of questions, okay, so this is good practice. And then number 2, it should be 100 grams, because now remember the mass should be conserved, and that is why. Okay, so we're going to carry on, okay, Leviosa's experiment, okay. So the water then cooled down, okay, and after the water cooled down, he weighed his water, okay, and at the beginning, he just had water, 100 grams of water. This water traveled through this pipe, and at the end of the experiment, he weighed it, and only 80 grams of water was weighed. Its mass went to 80 grams. Now, what are your first thoughts here? What do you think might have happened? Why do you think it's gone from 100 grams of water to 80 grams of water when you've heated it up? So Sam, I'm going to say Sam's answer, okay, to help some of you. So Sam has said that 20 grams has evaporated, okay. Now he is right in some aspects there, okay. So when you boil water, it's changing the state from what? Does anyone know? So it's going from a liquid to, someone tell me the answer. You boil water from a liquid to a what? A gas. Well done, Hamish. Yeah. So we boil water from a liquid to a gas. So Sam is right. That water has now evaporated. But so where has that 20 grams gone, do you think? Why hasn't 20 grams of the water cooled back down? 20 grams of the gas of the water cooled back down to a liquid? Okay, so I'll just put the questions on there that I've just said. I forgot to put them on. So have a little think. So why does the water now have a mass of 80 grams instead of 100 grams? Sam is right. Some of it is evaporated, but where has it gone? Not sure? Okay, let's have a look then. So into there. So bearing in mind this pipe, he put a metal pipe in to collect the water, okay? Leviosa then realized, oh, I've measured the water that's cooled down, but I haven't taken the weight of my pipe. So what do we think? Okay, he then recorded the mass of that tube. What do you think was the mass of the tube? What are your guesses? So we had 100 grams of water. Then he measured it at the end of the experiment and there was only 80 grams of water. Then he remembered he hadn't measured the mass of the tube. What do we think happened there? So Leviosa, he discovered the tube had a mass of 20 grams. Yeah, well done for those that sent in that message. Yeah. So, and what's 20 plus 80? That's 100 grams, isn't it? So this supported his theory of his conservation of mass. Okay, so this time, so at the beginning we looked at ice. Okay, the ice melting into liquids. Okay, now we're looking at the other way around. The water heating and turning into gas and then cooling back down into water. Okay, in both of those experiments that we've looked at today, mass has always been conserved. Okay, so some practice questions. How long we got left? About 5 minutes. Okay, so I'm going to give you a few minutes, okay, and then we'll go through the answers. I'd like you to answer questions 1, 2, and 3 just to finish off, okay? What theory states that matter cannot be created or destroyed? What is the theory that we were looking at? The conservation of mass states that what? What's important about mass? And who found evidence to support the conservation of mass? You can send in your answers via the chat. Well done, Hamish. We've got your number 1. Okay, so yeah, the answer to number 1 is, oops. Oh, did I not put the answers in? Oh yeah, I have. Yeah, so number 1, which most of you have done already. So the theory of the conservation of mass states that matter cannot be destroyed or created. Okay, it's always conserved. Number 2, yes, well done. If you put mass always stays the same, that is very similar. Okay, the total mass of reactants and products, okay, using our scientific words, must be the same in a chemical reaction. Otherwise, matter cannot be destroyed. So mass is always conserved. It's still correct. Yeah, well done. And number 3, yes, well done, Hamish, Leviosa. So who found evidence to support the conservation of mass? That was Leviosa. Okay. And lastly, to finish off with, okay, these were the questions that I said at the beginning. We were talking about a theory. Okay, so 4 questions there. Okay, just to finish up with, just to recap our brains from the beginning of the lesson. So thinking of theories, number 1, what makes a theory different from a guess? Number 2, what makes theories better than others? Number 3, what are some examples of theories? And that can be any example. It could be one that you've heard today, or it could be the one that you've heard before in the news, or when you've been reading something. That could be anything. And number 4, how can we use experiment to find evidence for or against theories? Okay, last minute, and then the final bit of the lesson. Just sending your answers from 1 to 4 via the direct message, so we don't have to copy each other's answers. Okay, let's wrap up this lesson. So does anybody want to tell me what makes a theory different from a guess? Does anyone feel confident at the end of the lesson to unmute their mic and say it? Or if not, you can write it in the chat. I'm just going to wait in case someone is typing. Yes, theories are educated and supported by evidence. Very well done, Sam. That's exactly what I've got. Theories are supported by evidence. Oh, what was our number 2? Our number 2 was what makes theories better than others. So what makes theories better than others? A good theory is a theory that can explain events well. That's meant to say there's a typo there, not will. Events explain well, and is supported by evidence. Okay, so remember, it's always referring back to that evidence. Okay, so that's how we can tell whether it's a good or bad theory. If a theory doesn't have much evidence, then it's not a good theory. Number 3, what are examples of some theories? Okay, so I've just put the ones that we talked about at the beginning. So we've got Newton's theory of gravity, we've got a theory of evolution, and the theory of a spherical Earth. And lastly, to finish off with, number 4, how can we use experiment to find evidence for or against theories? Experiments can either be measurement, observation, or through counting. And we've had examples of that today. So Sam said about the spherical Earth, those observations, okay, that scientists have done from space. They observed that the Earth is spherical, okay. Measurements, we've looked at that today on our screens of our ice and our beaker. The mass was the same, okay. So that's how experiments are done for theories. So that is the end of our lesson. Oh, I'm just running 2 minutes late, so I do apologize. So that's our science lesson today. Okay, same time next week. That was today was a bit different because I don't know you guys, okay, and you're all in different year groups, year 7, 8, and 9. So I just wanted to see who knew what and where we were at before I continued with the rest of the lessons for the rest of the summer. So well done everyone today. Thank you for participating, and I'll see you next Thursday at 9 o'clock. Enjoy your days.